Hello, everyone. I'm John Clark. I'm the president and CEO of Masterclock. Like Marla said, I'm 36 years old. I have the privilege of running a company that has products in over 110 countries around the world. We do everything from launch to rockets for NASA to timestamp stock transactions to make sure that the air traffic control system works well whenever you're flying through. So we've got a lot of experience with when time works well and when it doesn't. So today, I'm going to talk a little bit about behind the clock. So this is methods and applications of timekeeping. What's going on to get that time on the clock in front of you? And how do you know if it's right, if it's wrong, or what that may look like? Then afterwards, Demetrios is going to talk about theories of time. So not just what time is it, but what is time? And what does it mean when we say what time is it? And how does that affect you? So a little bit of a deeper talk. So I'm going to try to run through this here pretty quickly. So we'll start about what time is precisely. It's everywhere. So this is from Homeland Security, put out a list of some of the different industries that are affected by time. The way that you drove here is based on time. The cell phone you use needs accurate time in order to operate, and it has to have an accurate local clock. When you use your credit card to pay for this, that transaction needs to be traced back to a central reference so everybody knows exactly when it happened and that it was real. The power grid, security, everything relies on distributed accurate time to make sure everything works in coordination. So time is precisely everywhere. I'm going to talk real quick about some early timekeeping and how did we get the accurate clocks that we have today. So one of the initial uses of time was for navigation. Back in 1714, Britain offered a reward for a way to accurately predict longitude at sea. In order to predict longitude, you need a really, really accurate clock. Now, why is that? Well, when you're sailing, if you know what your local time was when you left, and you're carrying that with you, and then you can look up and you can see what angle is the sun after you've made some portion of your voyage. Using the angle of the sun, you know what your local time is. If you know what time it was when you left, 1 hour equals 15 degrees of longitude. And so by tracking your time as you're traveling, and then knowing what time it is locally, wherever you're at, you can actually figure out how far you've come from your original source. And prior to this, it was extremely difficult when you were trying to navigate the seas to figure out what your longitude was. They had some lunar ranging methods. But really, if you really wanted to do it accurately, and you're thinking about leaving from over in Europe and trying to cross the Atlantic, a very small difference in time can really throw you off. And so the Brits really, really wanted to figure out, how do we get a better clock so we can accurately estimate longitude? Which led to a new course for clocks. So a British inventor named John Henry Harrison built a number of clocks over the next 50 years. At the time, the prize that the king had put out was 20,000 pounds, which is $3.5 million in modern terms. So it was a very hefty prize if you could get it right. And he finally, on his fifth device, and after a lot of harassment, I got the final portion, the final 8,000 pounds from the king 50 years later. He designed a clock, was spring-driven with timing intervals derived from gear spacing on the balance wheel. And there's a design for it of his fourth version that he did. And I'll go into what we mean when I say maintains time through oscillation in just a second. But it's pretty crazy. This little picture of this clock right here is what transformed the ability for nations to traverse the seas. And it became a very historical timepiece for us from Mr. Harrison. So when we talk about oscillation, what do we mean by an oscillation? An oscillation is a periodic fluctuation based on a change in energy. And so you can see here, as the pendulum goes, it's causing the clock to tick. The resonant frequency, as we call it, was a state when the system most easily transfers energy between storage modes. So in this case, kinetic and potential. It's transferring its energy between kinetic and potential, and we say it's resonating when it does that the most easily. And that's an important concept we'll get to in just a second. And so the way that the Harrison clock worked was it was able to create very consistent oscillations, which becomes your timekeeper. So when your ship is going off on its own, you're measuring those intervals through this mechanism. And so now we've got ships with accurate clocks, so you can figure out how far you are from your source. But then transportation got a little bit more complicated. We got into the railroad era. Now it's not just as important to know how far you've come from your source, you need to know where the other train's at. And the other train needs to make sure it's not where you're going to be. And if you don't get the synchronization right, you end up with that. And so the railroads led to a huge need to synchronize these distributed stations to make sure the trains weren't working in contrast with each other. And so they had to work on the concept of time transfer. So what Harrison did was he invented a way to know the time and to hold the time with you as you go. But sometimes you've got a clock and you want your clock to be more accurate. Let's say it's been drifting. We do what's called time transfer. It's a scheme where multiple sites share time and frequency information for synchronizing distributed clocks. So in the example of the railroads, what does that mean? They would take a clock similar to Harrison's H5 clock, and they would actually ride the trains. And when they got to each station, they would stop and they would set the station time. They would ride to the next one, stop, set the station time. And if they did that with enough frequency, they could keep the clocks from drifting too much. So even if they didn't have as good of a clock as Harrison, by updating it with some regularity, you could keep the time correct and keep the trains running and keep everybody safe. Well, let's look at the modern world. What if you've got an Internet of Things device? You can't really just bring somebody up with a clock and set the time on your Nest. So how does that happen? In this case, it actually requests the time from an online server. We call it a network time protocol server. It uses the received timestamp that it gets to set its local clock. And so whether it's this laptop or a camera or anything else in here, if it's connected to the internet, it can pull a central server that knows what time it is, receive that time, and then update its local clock. And just like a train conductor riding from station to station, it's all the same concept of time transfer. And by building really, really good clocks and getting better at time transfer, that's kind of how we enable this synchronized world that we live in today. So nowadays, where all can we get the time? I don't see any conductors on trains carrying clocks anymore. Here's a couple of different methods. You can use a dial-up modem if anyone still has one of those. WWVB, that's the signals coming out of Colorado. Have you ever seen those Skyscan atomic clocks? They're really listening to that radio signal to synchronize themselves. All the way to GPS. Most of us are pretty familiar with GPS, the Global Positioning System, which is really nothing more than a very advanced use of time and time of arrival, which I'll show you in just a second. So we get the time, and then we say we sync our local clock. And let's talk about what we mean by a local clock. There's something called a quartz oscillator. And a quartz crystal, when you grow quartz, crystals of the same size resonate at the same frequency, meaning that when they're at their state where energy most easily transfers between states, two crystals of the same size have those same properties. So if you can put two quartz crystals in two different devices, they should keep a pretty similar heartbeat for both of them. Because quartz has low swap, as we call it, size, weight, and power, and it's inexpensive. It's got low cost. Quartz oscillators are basically everywhere. In the car that you drove here, in your cell phone, and most cell phones, not some iPhones don't, and all sorts of devices, the heartbeat of it is actually a piece of quartz. And when we apply some current across the quartz, it causes it to oscillate, which becomes our clock. So there's an example of what a 16 megahertz quartz crystal looks like, which you'll find everywhere from cell phones to tablets to watches into vehicles. We've all heard then about atomic clocks. Well, what's so special about atomic clocks compared to all these other oscillators? When we talk about the resonant state, in this case, we're saying the electron transition energy, the amount of energy that it takes for a set of cesium atoms here at McHenry County College is the same as if you were on Mars. And so that consistency, just like two quartz crystals of the same size have the same resonant properties, atoms do the same thing. So what we call the resonant transition frequency is achieved. That's the frequency that you're applying to an atom in which it is most easily changing states for its electrons. We say that it's a resonant frequency for that atom. So here's a brief little diagram. All an atomic clock is really doing is exciting atoms. In this case, it's cesium. And it's exciting those atoms until it gets to its resonant frequency, which again, any cesium anywhere in the world, or rubidium or strontium or whatever the element may be, is going to act the same. Once we know that we've got it at its resonant frequency, we take that information, we transform the value, and then we use it to synchronize a quartz oscillator. And we get that quartz working in cahoots with the cesium. And so now that quartz crystal is tuned to the resonant frequency of a cesium atom. And it doesn't matter where you're at. It's going to tune to that same resonant frequency. And so you end up with great matching clocks, depending on what elements you're using. So whenever you hear about atomic clocks, it's just a really, really fancy way to discipline a quartz oscillator at its core. But these things are pretty cool. We use a lot of the element rubidium instead of cesium because it's easier to deploy. There's less rules about it. It's cheaper, smaller, and all sorts of things that we like as practical timekeepers who have to make money from time. So GPS, we all use GPS. Is it global positioning system or global precision clocking system? So I'm going to go through just 4 quick highlights of how GPS works, and then I've got a little animation that should help to describe it better. So inside each of the GPS satellites, you've actually got atomic clocks that are doing exactly what I talked about, and they're getting their quartz oscillators so that they're perfectly, resonating with all their atomic elements. Your ground receiver is listening to the signal from the satellites. The satellites are broadcasting, here's what time it is, according to all my clocks that I got, and here's where I'm at in the sky. Your receiver is calculating the time of arrival for how long that signal took to get to the receiver from the satellite, and that's how far you are from that one satellite. So imagine in all these satellites, there's atomic clocks, and they're saying, here I am, here's the time, and it's all going down to this plane. It's flying along the East Coast. And so that plane is calculating how far is the distance from any one of those receivers. And remember, that distance could be on a circle. Once you trilaterate and find where all those circles cross, that's how you find your location. GPS is nothing more than clocks checking time. So next time you hear about navigating by GPS, you're really navigating by atomic clocks. So you're welcome. Thank you, Demetrios. One of the things that you'll hear about right now is the concept of GPS jamming. GPS, when it was turned online, everyone started using it. We used it to navigate here. You use it to catch your Pokemon Go. It's used to do so many different things. We almost take advantage of it and forget that it might be vulnerable. What happens if you can't get GPS? What happens to your phone? What happens to your navigation? I know there's a new Julia Roberts movie that's out that's got a lot of people scared about what happens when these systems go down. That's very real. Jamming's not always good. I like this little meme. This printer is now called Bob Marley because it'd always be jamming. In this case, though, it's the Russians. The Russians suspected of jamming GPS signals for thousands of airline flights, and that's real time. These planes are not designed to have their distributed heartbeat broken up, and so what happens if you're a pilot and suddenly your plane thinks you're over there? It's not very good, and that's not what we want. So whenever GPS jamming and spoofing can disrupt location or disrupt navigation, local knowledge of time can help mitigate spoofing and overcome jamming using other sensors. Now remember, Harrison knew if he knew the time and he could see the sun, he could calculate where he was at. Well, in this case, you can use sensor fusion. You've got high-speed imaging, you've got your inertial measurement unit, which is measuring how you're moving, how you're tilting. You've got LiDAR, light detection and ranging. All these signals, all the stuff that's coming in, if it's all accurately time-stamped, it's all going to be coherent and it's going to make sense. And the more aligned those timestamps are between different devices that are making this local calculation, the more in coordination they can be. And so if you can't get everything synchronized to a central GPS, time source, how can you try to get the time source into the device? So in this case, the local clock is the heartbeat, which leads us to the current state where DARPA is currently pursuing a new clock, and they want a better clock. And I chose this because they called it the H6 program. And if you remember, our guy Harrison got up to his H5 clock, which was the final clock that ended up winning him the modern $3 million prize. DARPA is so desperate for a solution to this GPS problem, H6 is the spiritual successor to Harrison's H5. They want to remove GPS timing dependency, and they think it's the clock Harrison would build to solve today's tactical mission challenge of GPS denial. So just like the Brits back in the day needed to figure out how do we conquer this navigation challenge, we're in the same boat today where our GPS is being abused and taken advantage of. And so researchers like us are trying to figure out how do we make a better local heartbeat so that if you can't get GPS timing, you can still navigate and live your life. And so I keep talking about these clocks and how they're accurate, and they do, these various things. How accurate are we talking about with these? So the clock that received the longitude award, this was the H5 clock, it would lose 1 second every 3 days. And if you compare that to your wristwatch that you may have, that's not very good, to lose a second every 3 days. But back in the day on a ship that was moving on the ocean, that was fantastic, and that changed the game for them. So what about the clock for DARPA's H6 program? This is the new thing. They want to give a bunch of money if somebody can figure out how to do this. That clock loses 1 second every 20,000 years. So most of us wouldn't be around to point out when that clock had a fault. Hopefully some of our kids will be. What about the clocks in the current GPS satellites? Block 2 for the Demetrios of the world, not Block 3. That loses 1 second every 3 million years. And so hopefully we'll still be around as a society when we can measure one of those clocks losing a second. Today's best, at the University of Colorado Boulder, they've unveiled a strontium-based optical lattice clock. And I won't even try to get into what that is. But that's what it looks like, a cooler version of the Harrison H5. It loses 1 second every 39 billion years. That's a lot of math to figure that out, and we may never even be able to observe it doing that, but we know mathematically that's what it can do. These optical lattice clocks are what they're about to use to redefine the second, which is a big deal for the timekeepers like us. And so just very briefly, I just gave you all like the briefest summary of the history of timekeeping. The Brits wanted to navigate better. They gave a bunch of money. The railroads were breaking because nobody was on time. GPS worked really well. Now it doesn't. Here's some money. Let's get a better clock. So this is kind of the state of the art. We've talked about clocks. I've talked about keeping time. What is it? Can anybody show me time? Does anybody have time? We all have time, but yet we don't. I don't know. So for that, I'm going to go ahead and invite Father Time up, Dr. Matsakis, who's going to talk to us a little bit about what goes on beyond the clock.
If anybody thinks he can tell you what time is, he probably doesn't know. That's the number one step. In particular, this guy. But that doesn't keep me from trying. When I was asked to put it on the internet 25 years ago, I defined it as that coordinate which can be most simply related to the evolution of closed systems. There's a lot of things packed into that, some of which I will talk about further on. Nowadays, though, I'm thinking I would just go with this. That can be most simply related to a sequential ordering of events. A few weeks ago, I looked up Aristotle's definition of time, and I was pleased to know that it's very similar to this. It doesn't have highfalutin words like coordinate, but it's a basic idea. There are other people who have tackled the concept of time. For example, Thomas Aquinas, the saint. He said, if nobody asks, I know what it is. If anybody asks, I don't know. And then, if you read his book, like I have, he goes on to say, therefore, he's not going to pay attention to anything else anybody has written before him, but figure it out for himself. 4 or 5 pages later, he comes up with a definition of time very similar to Aristotle's. So let's get a little bit more modern. Time is nature's way of making sure everything happens at once. That's from Professor Wheeler that we're going to hear more about at the end of this talk. He claims he got it from a bathroom wall, but he doesn't say who wrote it on that wall. And also, it's been ascribed to these people but I'm going to go with Wheeler. A similar quote, because time and space are related, is space is nature's way of making sure everything doesn't happen to you. That is attributed to the same cast of characters. Now, I'm jumping a lot to fit it all in 40 minutes. I'm going to ask a question. What is light? And is this light an interplay between electric fields and magnetic fields? Fields are like, for those who don't know about this stuff, less mathematically inclined, think of them as force fields. And in 1861, Maxwell, a Britishman, showed that light was waves using Maxwell's equations. And I'm going to describe them to you the same way I described them to my children when they needed bedtime stories. So to put you at ease, I see one person nodding. You probably do. You ought to never mind that. So let's go on now. A guy called Faraday had discovered that if you change electric fields, you can make magnetic fields. That's how electromagnets work. A guy called Erlstead discovered that if you wiggle magnetic fields around or move around in one, it'll make an electric field. That's how Hoover Dam works. So Maxwell wrote down those equations and found he could get solutions where you change an electric field into a magnetic field back and forth indefinitely. And he called that light. I'm going to show on this diagram here. Here is a magnetic field going up. The electric field goes up at the same time. It's moving this way. And as it progresses down, you see the fields going up and in, interconnecting and intertwining. The killer fact was when he put in the math, like how much does the magnetic field change? Oops, we went to hit it twice, but it's okay. He found the math correctly predicted the speed of light. This was the most exciting thing in 19th century physics, that light was these little waves of things. But every answer leads to another question, and I jumped the gun there. They went to, if it's a wave, what's the ocean that the wave in? They knew its name, the ether. And that's really all they knew about it. And for the next half of the century, science was devoted to learning about it. Come to America, and these guys asked, what's the velocity of the Earth with respect to the ether? They did a very famous experiment called the Michelson-Morley experiment. And does anybody know what they found? 0. And that blew their mind, because the Earth is going 20 miles a second around the sun. So if it's 0 now, 6 months from now, they should see it going 40 miles per second the other way. And their data was accurate enough to measure that. They didn't see it. So this is the only time that the Nobel Prize was given for discovering nothing at all. Yeah, and people had ideas, like some said, well, maybe the Earth isn't moving. And Copernicus was wrong, but we had other reasons to know the Earth does go around the sun. Others thought maybe the Earth took the ether with it, the ether drag, but they could rule that out. It wasn't until Einstein came along that we had an answer. Einstein was thinking about this, and he asked the question, what would the light wave look like if you went alongside it? So imagine you're here when both fields are at a minimum. At that point, they're at a maximum a little further down, but when you get there, if you follow the wave to go down, the minimum's traveled with you. So all you see is 0. The whole way down, you wouldn't see any light at all. And if you were at the maximum of it, and you followed them down, you'd always see the electric and magnetic fields being a maximum. So everything would look stationary, and Einstein was really confused by that. I mean, how would it all work? What was wrong with Maxwell's equations? How could that happen? And he thought about it for a very long time, and he finally came up with his answer. You just can't do it. You cannot travel at the speed of light. And that was the foundation of his theory of relativity. It's called special because later he generalized it to include gravity. But for right now, gravity had nothing special in that. So he started with these principles that matter cannot travel at the speed of light. Light can, but nothing can go faster than it. And as a part of that, then you have to say all observers get identical measurements for the speed of light, no matter how fast and in what direction they're moving. Starting with that, he rewrote physics. He rewrote our concepts of space and time. They said that they get mixed up. We'll talk about that later. All these things we'll talk about later. And honorable observers will disagree about things. Now, by honorable observers, I mean scientists and engineers that during our experiments inside of laboratories, and of course, who don't fudge their data. So they'll disagree about what's stationary. Basically, all test equipment thinks it's stationary, how long length is, and what's simultaneous, as in what came first. And also, how fast time moves, but any McHenry County College physics student can calculate what different observers will observe. You tell the student how fast they're going, and the student will tell you what their space and time concept is. What does a freshman say? A stationary observer will think the yardstick shrinks, the mass is greater, and that's where E equals mc squared come from, and that its time runs slow, and was at the clocks. This was first seen in cosmic rays, but the Clincher experiment happened in 1971 when, at the Naval Observatory, a technician who I knew, in fact, I was his boss for a very short time before he retired. They took some clocks from the observatory, flew it on a jet plane, flew it around, and when they came back, the time on those clocks had differed from the clocks that stayed behind by just the amount that Einstein predicted. So maybe you're all familiar with the fact that nothing can go faster than light. You've seen enough science fictions and stuff. But I'll tell you a story from my childhood. When I learned about this from junior high school, reading some book, and I told my brother about it. He's right there. And my brother was a budding lawyer, and he said, wait a minute, I got a counterexample. I can prove you wrong. If you have a cowboy riding on a horse and he shoots a bullet out, that bullet will go faster if the horse is galloping than if the horse is standing still. Well, why do you say that the speed of light on a modern cowboy, that was modern for when I was young, would driving a car, that would be the speed of light to him and me on the grandstands? I would see it as the speed of light too. And the answer is, yes, that's right, because I say his sense of time is screwed up and space, and he says my sense of time is screwed up in my space, but we both put them together to agree on the speed of light. And actually, Einstein's equations also tell you that bullet also goes faster, but if the horse is running, it doesn't go as fast as you might exactly think. It goes a little bit fast, a little bit less fast, depends on the ratio of the speed of the bullet to the speed of light, which is very small. I probably lost you with that. But what's left was time then? Einstein left a bit of time, causality, cause and effect. He stripped time down to causality, and that's what was left to be real. So events, he said, are the same for everybody. My talking to you is an event. Different observers can give him different times and say they're in different places by their own coordinate systems. And that doesn't matter. They have to agree on events. And if light had time to go from one event to another, then that event can obviously influence it. So all observers will agree about which happened first. And some will think they happened at the same place, others will not. But if light did not have time to go from A to B, then event A cannot influence event B. And observers will disagree about which was first, and none of them will think it happened at the same time. This is so important, I'm going to say it again. Time order is inseparable from causality. And I'm going to give you a quiz. Which event happened first? Event 1, Einstein gets the Nobel Prize. Event 2, a star exploded in the Large Magellanic Cloud that goes around our Milky Way galaxy. And the newspaper said it took 200,000 years to reach us. We saw it in 1987. So maybe by a show of hands, how many people think event 1 happened first? I've got a few hands. So the rest of you must think event 2 happened first? Very good. It's a trick question. Because whatever you say, you're right if you're traveling at a certain speed. So if you were at the speed of the Earth, then indeed, the people who raised their hand for event 2 would be right. That would happen first. That's what their measurements would show after they allowed for the speed of light. But if you were in a spaceship zooming towards the supernova, then your space and time would be screwed up. So even after you allowed for it, you would think that Einstein got the Nobel Prize first. It's undetermined because the supernova could not have influenced just getting the Nobel Prize. The signals did not arrive until afterwards. But everybody would agree that when we saw it, then that was after he got the Nobel Prize. Well, let's go on. I forget what the next slide is. Gravity. Einstein took on this question. I repeated that again. He took on the next question, gravity and time. You might have asked your mothers when you were little this question, if you learned about gravity. I mean, what does it mean to say that the Earth down here could pull on an apple up there, let alone up to the moon? How could that happen? And you probably didn't get a good answer. Isaac Newton also had trouble when he came up with his laws. A lot of people didn't believe him. They thought action at a distance made no sense. And what was his answer? Well, here are my equations, and they give the right answer. They describe what's happening, so get over it. It's true. And but Einstein also had trouble with that. And after much deliberation, there was his answer. They call it the general theory. Took him 10 years after he did the special theory. Let's give a review now of how the special theory, as it applies to this. The special theory takes place, you assume what we call flat space, where the geometry that Euclid derived and you learned in school, that applies. For example, the sum of the angles in any triangle is 180 degrees. And in that concept, and in the concept of special relativity, a straight line can be defined as the shortest distance between 2 points. Light moves in straight lines. Matter wants to move in straight lines, but it can get pulled by a force, like electricity or gravity or other forces that the physicists know about down at Fermilab. So that's the special theory. But then Einstein thought, what if space is curved? And there's the picture you just saw. It says, what if space has some funny curvature and we don't know it? We're thinking now it's a curvature that you could be aware of if you were a 5-dimensional creature. We have the 3 dimensions of space and one of time, and we know they get a little bit mixed up in the special theory of relativity. But if space had a curvature that you could see as a 5-dimensional feature, you could also, in theory, measure it by the angles of this triangle. You can see that they're not going to add up to 180 degrees. But you still accept the fact that things move the straightest way possible. So he said gravity was things trying to move straight in a curved space, just like a car going on a racetrack, and it's at a slant. The car's going to do some funny things, or if you're going on a bumpy road, you'll do funny things. But they will do it to wiggle as little as possible. That's the principle of least action. It's also called the law of cosmic laziness. Now, I'm going to give you an example here. Let's consider an ant, a 2-dimensional ant on a 2-dimensional sphere. In this example, the ant is unaware of any distance out of the sphere or in the sphere, just a 2-dimensional thing. And she's trying to walk in a straight line, but she ends up going in a circle. how would she interpret this when she comes back where she is? She'd say she's going in orbit around something there at the top or in the center, which is exerting a gravitational pull. And that gravity is what made her come back to where she started from. But you and Einstein know, no, it's a curved space. This then is generalized mathematically, and it gets things that when I did my random survey of people coming in, you all know about. Black holes, that's for the extension of it. And black hole space is very, very curved, and you can't get out. And also, if you go near a black hole, your time slows down. In fact, if you're on the Earth, the time is slower than if you're out in space where there's no gravity pulling on you. And so that all comes out of the theory of relativity. We think there are about 1 billion black holes in our galaxy. I remember when we don't know of any, and when the first one was discovered by, I like the name drop, you should do when you get old. The guy at the next desk, when I was a grad student, was the first one to observe a black hole in the center of our galaxy. And also you may have heard about wormholes, which are when this end of the black hole, where space is very curved, opens up into another part of space-time. Those we know of none. And we can solve the equations of relativity, but it generally takes a special kind of matter that has negative pressure. Most matter pulls out, negative pressure would tend to pull in. So we don't know how to do that. And here we are entering what I call metaphysical time. Everything I've told you about before, everybody agrees with. Everything I'm going to tell you about now, except the very next slide, which is the setup slide, people argue about the nature of time and time travel. So now I'm going to talk about antiparticles. Every element, that went away, antiparticles. Every elementary particle has an antiparticle and combinations of them, like hydrogen, there's antihydrogen. We've made it, sort of like the opposite of it. And that has the opposite electrical charge. So in an electrical field, they move in opposite directions. If there's a magnetic field, they will be pulled in opposite directions because they have opposite charges. But their masses are the same. And when they meet, they annihilate each other, converting mass to energy and following the law E equals mc squared. And we see this all the time in cosmic rays. Down the road at Fermilab is very common. I'm going to submit to you that antiparticles can be considered to be particles going backwards in time. It's not my idea. It was by someone called Feynman that we'll hear about later. He also was in the movie Oppenheimer, although he wasn't identified. He was the guy playing the bongo drums at one point. And he said, he also was the guy that when they were all putting on things to protect their eyes from the first test, he said, I don't need any glasses. I don't need those glasses. I did the calculations. I know it won't hurt me. So he didn't wear them. So in this diagram here, this is time going that way. That's one dimension of space, just to show it. Typical interaction would be an electron's going this way. It's got a negative sign. It meets an anti-electron. It's got the opposite sign plus. They annihilate each other, make a gamma ray. The gamma ray decays into an electron and an anti-electron. A very common interaction. Feynman looked at this and said, there's another way to understand this. The electron is moving forward in time here. It gives off a gamma ray, and then it starts going backwards in time. So we see this electron going backwards in time, and we call it an anti-electron. And then at this end, the gamma ray hits an electron going backwards in time, which we call an anti-electron, gives it a jolt, and then it becomes an electron going forward in time. So there's time travel hiding in plain sight. And he went further. He said, well, that could be happening all the time. And it would answer an interesting puzzle in physics, which is, why do all electrons have the same mass or weight, And why do they all have the same charge, plus or minus? The answer is because they're all the same one. So to show that, here's an electron, gives off, becomes an anti-electron. It gets absorbed, becomes an electron, gives off, becomes an anti-electron. And here it comes in here again, because this is 3 dimensions, can loop around, and it absorbs this photon, and then it becomes an anti-electron. So it's the same one traveling through all of this. Well, that's cool. So if I tell you, there, time travel is done, you're not going to get very excited about it, right? I mean, if you want to do time travel, you want to go back in time and maybe do the perfect crime, come back to the present and enjoy whatever you did. Or you'll go back in time, maybe a few of the saints among you, go back in time and stop Hitler and then come back, right? That's time travel. And that's what I'm going to talk about next. So sexy time travel is time travel for you, but nobody else. And also for your memories. They got to go with you. So the question is, does relativity allow time travel? The answer is a maybe. And I have to warn you, I understand this is going to go on the internet. If you're watching this later on the internet and you're in China, it might get cut off because they have banned anything that describes time travel because it disrespects history. But we can continue. We're safe. The first example would be tachyons. They're a standard feature in Star Trek. They haven't been observed, but yes, people have looked for tachyons. What's interesting about them is that they can only travel faster than light. I just told you nothing can travel faster than light. Oh, okay, you jumped the gun on all this. Let's leave it then. No secrets here. They're allowed by the equations of relativity. Einstein thought they were possible, but to make it all work, they don't have mass as we know it, pounds or kilograms. It's imaginary than the square root of -1. And if they gain energy, they go slower. So if you have a tachyon going faster than light, and you give it energy and you give it energy, you'll slow it up. You have to give it an infinite amount of energy to bring it down to the speed of light. So if they exist, can they be used to communicate with the past? That's another thing that people argue about, because some people say emitting a tachyon looks just like absorbing an anti-tachyon. So they say, no, you can't. Einstein actually thought they could, although he didn't get too excited about it. Another possibility is wiggling wormholes. This came from Carl Sagan. I think you know who he was, right? He wanted to write this book called Contact, which is a great book to read. The movie is almost as good. And he asked Kip Thorne, here he is, announcing the discovery of gravitational radiation, for which he later got the Nobel Prize. But at that point, he was just a normal physicist. And, well, not a normal one, but he considered the matter and told Carl Sagan, yes, I know a way we could do this. And here is his recipe. You could try it out in your labs if you're in the physics department here. First step, create a wiggling wormhole. That's all. Wait a little bit, then cross to the other end, get off, let it wiggle some more, go back, and you can return home before you left. You cannot return home before you made the wig hole, but you can return home before you got on it. The only problem is how to make the wormhole. You're going to need to get exotic matter. The only way we know how to do it, and there are also some people who say that if you put mass in the wormhole, you will destroy it. So you've got to solve those engineering problems. But once you've done that, away you go. Now, if you could do that, it leads to an important paradox, which you may have heard of. It's called the grandfather paradox, which is what happens if you go back and kill your grandfather 10 years before your father was born. Then there's no father and no you. Nobody would ever go back and kill their mother or grandmother. So this is why they got men here. So how do you get around that then? How do you get around that problem? Well, Stephen Hawking, who many people consider to have been a successor to Einstein, came up with an answer, very Einsteinian. He said, you just can't do it. And he called that a fancy name. Oops. What's going on here? I've lost it. the chronology protection conjecture. Let's assume he's right. You cannot go back and change the past. Does that still mean you can't do time travel? No, you could. If you could do it, and you had to respect this rule, I can show you one way. You just got a glimmer of that before. Pass an idea to your past self. So here you come along, a normal person. All of a sudden, a future you appears in a time machine and gives you a great idea. You patent the idea. Then you come, oh, whoa, let's go back one year. You come along there, and then you remember to hop in the time machine, go back and give the idea to yourself. And then next time you come here, you keep going. Now you've got the patent, and you can enjoy all the wealth of that patent. And the question would be, what's wrong with that? Nothing. You've done time transfer to fulfill the present. You can enjoy all the benefits of that idea. Now, here's another wrinkle to that. What if, can I do it? Yes. What if, at this point, somebody comes along and tells you that idea? And then you could go over here, go to your time machine, go back, and now when that guy tells you the idea, you say, that is a great idea. I patented it just a while ago. Now you got the idea, and you still got it, and you can go. And then this person finds out that you did this. What do you do then? I tell you what you do. You call my brother the lawyer. He'll get you out. He's a very good lawyer. We're moving along now. I'm going to talk about quantum mechanics. When I did the survey, very few of them, you knew it. I'm not going to tell you much about it, just enough to talk about time travel and timing and all of that. Do I have the Heisenberg uncertainty principle is something that I will now describe. And I will tell you, by the way, that Feynman, the person I gave earlier with the antiparticles, he said what I said about time. Nobody understands quantum mechanics. If you really do, then you think you do, then you don't. So he said that you could not simultaneously know the position and velocity to any accuracy at all. There's a limit to what accuracy you can do to measure those things. It's called the Heisenberg uncertainty principle. Hit the wrong button there. And it's got a numerical number. The product of the uncertainties always must be greater than Planck's constant, which is a very small number, but they can never be zero. You can't get absolute knowledge. And that could be, Niels Bohr called that complementarity. And he said the position and velocity are complementary. They both tell you something, but neither tells you the whole thing. The whole thing is something else. And he generalized that to other things like energy and time, which we'll talk about again. By time now, I thought of being like the half-life, and energy is the energy of a transition that John was talking about. And to give you a real-world example, Niels Bohr was really big on real-world examples. A cocktail party. A guy comes up to a girl and says, I am here for you. And what does she say? Right. And there's even a song about that. Where will you be tomorrow, right? You know that song. I think it was a big one when I was a kid. So let's go on to the next thing of quantum mechanics, quantum unpredictability. It comes out of the uncertainty principle. There's no way to predict any outcome, any out at all with 100% accuracy. You can compute the probability of an outcome, but not the result. It's always less than 100%, no matter what you do. Einstein was very much against the inferences of this. He thought, yes, it might be right, but it's just our ignorance. If we knew everything about it, if we could do the right experiment, we would know 100%. His famous quote is, God does not play dice with the universe. He and Niels Bohr had it arguing in many conferences after conferences about it. It never got settled in their lifetimes. But in the 1960s, we got the Bell theorem. Bell at CERN showed that you can design an experiment to test if the properties exist before they are measured. They did the experiment, and Einstein was wrong. We really can't know. There is no way to know. And an example of that would be the Schrodinger's cat paradox. Schrodinger said, what if you put a cat in a sealed box, tightly sealed box, and you have a radioactive element in there and a vial of poison? If the element decays, it'll trigger the poison to be released and kill the cat. So you wait one half-life, this is waiting a half-life right there, and you open the box. If it's a half-life of the radioactive element, then there's a 50-50 chance that element would have decayed. That's the definition of a half-life. So there's a 50-50 chance you open the box up and find this dead cat and be cursing Schrodinger for this stupid experiment, and there's a 50-50 chance that you'll rescue the cat. The question is, if you find the cat dead, when did the cat die? Did it die when you opened the box? Did it die sometime in there, and you don't know what it was because you didn't open the box? And the answer is, it really died. I mean, you knew it was dead when you opened the box, because that was what the Bell theorem told you. It was undetermined before then. There's another way to look at this, though. When you open the box and do the experiment, that's an experiment now, just opening the box, you split the universe into two. In one universe, you're there with the cat dead, and the other universe, you're there with the cat alive. That's called the multiverse. And that happens every time there's a quantum thing. The universe just splits and splits and splits. And is there any way to experimentally measure that? We don't know of a way now, although in the science fiction it happens a lot. I mean, it always gets restored at the end. You go to the multiverse and Dr. Spock has a beard, or this happens. But maybe you could make some kind of a wormhole thing and connect, but we don't know how to do it. This leads to a question then, does every possible now exist? And in fact, quantum calculations, this is why Feynman got the Nobel Prize, for showing that if you really want to calculate anything, like how light interacts with matter, how atoms interact, you have to consider all possibilities, no matter how absurd they are, and you assign them a weight, and that weight is not a simple number, a probability. That's not a simple number. It's complex, like square root of -1. And you do all the math, and if you do that, you can explain everything just right. So in the example of the Schrodinger cat, one possibility that you look into is that the cat was taking a nap the whole time. You got to figure that in. Another possibility is he snuck out, have a good last night with his friends, and then came back. And you have to put that into the computations too. That has a very low probability. They call this quantum tunneling. And there's even another possibility you could have, that after that night with his friends, he just didn't come back. And all that has a certain probability. So maybe all of these then exist. If they all have to go into the calculations, every possible now exists. All of the examples that I told you happen to some level, and space and time are just humans imposing an order on that. The events that Einstein talked about are just when atomic particles, like all these particles, all of us, are near each other, and you can order it with another event when I'm on this side of the podium, and we just connect them up so that it's minimal difference, and that's space-time. And sometimes there's more than one way we connect them, and that's the multiverse. So that's a real possibility for all there is to life. And the artists know about this. You probably know about this painting, right? Nude Descending a Staircase. It's in Philadelphia. That's the basic idea. There's a lot of interplay between the art in the early 20th century and quantum mechanics and relativity. There's another extension of quantum mechanics, which is virtual particles. These come out of nothing, which violates conservation of energy, but they quickly disappear, so it's okay. And the The larger their energy, the quicker they disappear. So there is no such thing as empty space anymore in quantum mechanics. There's all these things appearing and disappearing. And yeah, we have detected their presence. This actually is called the Casimir effect. It's a test, and I don't have time to talk about it. But there's also the Lamb shift. You can look those up if you're interested. And we know they exist. And this leads to another thing. What happens if a particle comes out, then it's a black hole? Then inside of it, space and time are screwed up. And then it disappears. So that's called the quantum foam. And it occurs on a scale way below us. They call it the Planck scale. Very small size, very small energy, mass, and they don't last very long. But if you could observe on that scale, you would no longer see the continuous space and time as we know it. You just see total chaos. You could not have a clock down there that would work, or it would be a bananas clock. Certainly not one that John would sell would work down there. Which means, taking that to the next level, space and time must be accidents of nature. Just like the color of an object isn't fundamental to it, all red things aren't the same. For example, it just depends on what wavelength the thing happens to reflect. Or maybe you call it an emergent property, like music. It's not a fundamental property of sound. When I was a kid, I thought the Beatles were music. My parents thought it was just noise. And now, some of the new music that my kids do, I think is just noise. So, in the same way, space and time are not fundamental quantities, because in quantum foam and black holes, they lose their meaning. So that real physics, real reality is deeper than that. Who came up with that? The same guy that was writing on the bathroom walls. So he is pretty good. We're winding up the talk now. I'm going to address some of the questions that people often ask, like, when did time start? Did it really start at the Big Bang? Stephen Hawking says, yes. It makes no sense to ask what happened before the Big Bang, just like it makes no sense to go to the North Pole of the Earth and ask which way is north. You can't. So it just started there. But that, other people don't follow that, and they speculate. What happened before? What caused the Big Bang, for example? Sometimes they think there's these multidimensional things, not 3 in time, but maybe 100 dimensions, and they sort of collide. They call it brains. What's left is, it's not brains like brains, but brains maybe like membranes. They correct, and we are that little intersection of 3-dimensional world. The Big Bang came out of that, and mass. Maybe it's a scientific experiment. Maybe they collapsed them to see what they would do, and I hope they don't reject it, if that's what it is. Or maybe time started just now. Dinosaur bones, Stormy Daniels, and all. Boom. That could have happened too. There's no way to say it didn't. There's an extension of that called Boltzmann brain. These are real brains, which is, if you want time, it's more likely, if time started right now, it'd be a vacuum fluctuation. Do you really want us to have a vacuum fluctuation for the whole universe? How about one for just your brain right there? And so your brain just came into existence now, and it's perceiving all of us, and it will quickly disappear, but you won't know it. I mean, you'll go away, everything. They call that could be on, but it was shown that it's actually more likely to create a universe out of nothing than a single brain. There's arguments about that. Let's go on now. If we didn't know when it started, can we guess where it will end? Maybe it'll never end, right? That's what people would like to believe. They used to think it would end when the universe collapses on itself, called the Big Crunch, and maybe it'll rebound again, something like that. But now we know the universe is expanding faster and faster. We don't think there'll be a big crunch happening. Let's see. Maybe with those brains I talked about will separate, tearing the fabric of space-time. That's called the Big Rip. Or maybe it'll end with a whimper as the universe expands to a dilute gas. I'm going to talk about that, but first I got to talk about the universe. This is the universe as we know it. It started with a Big Bang over here, and at that point, nothing was fixed. Everything was in fluctuations. The laws of physics as we know them didn't exist. We didn't know anything. We can't even imagine what was going on. But we know that there was a period they call inflation. It was a very small time by our scale, but in that time, the universe zoomed open exponentially, and the laws of physics got set. Fields came to their values. The strength of the electric field got determined. The mass of the electron, the Higgs field, all that stuff. And I probably don't have time, right? Running low on time, to talk about the rest of the universe from there. But there was a dark ages when we couldn't see stars and they burned through. The great age of star formation happened about here. And we're here in this thing with the universe expanding faster and faster. It's accelerating out. We've only known that for about 25 years. So what will happen then over here? What do we think? Well, the outcome with the highest probability is, where are we now? Oh, did I not show that? Did I go backwards? Here. The outcome with the highest probability is that the space will just keep expanding faster and faster, and that means less density, less stuff will be in any one bit, and in a Google of years, what will be left with? We'll have lost contact with our neighbors because light even from other stars won't make it to us. The light will come off, but the space is zooming faster and faster. The light can't keep up because it can only travel at the speed of light, but space can expand all at once. So we'll lose contact with all of that, but will we even know it? Because everything will have decayed. Hawking showed the black holes can decay. Protons are believed to be able to decay on those large time scales. We haven't seen it yet. The universe will be a dilute gas with small fluctuations. Entropy is randomness. The small fluctuations around it. It's called alternately the heat death or the big freeze. And what happens to time? Well, there's no way to measure time anymore. The entropy is maxed out, as I like to say. So there's no time anymore. We've lost time. And that's pretty depressing, right? I mean, who likes that? Who wants that? Nobody. I didn't think so. Oh, one. Okay, good. Yeah, I can get you some ways, some hope here, because after all, science got us into this jam. So science can maybe get us out of it. The most likely, first of all, doesn't always mean very likely. If I flipped a coin 100 times, the most likely possibility would be 50 heads. But it's far more likely that it will not be 50 heads, some other number. So is that grasping at straws? Yeah, but I'll show you the straws that we could grasp at to make this happen. Maybe our physics is wrong. After all, a lot of what I told you, almost everything, nobody believed 200 years ago. And in the next 200 years, they'll be laughing at these antiquated theories that I'm talking to you about, and you guys paid money to come in here. There could be new physics that emerges when the universe gets very much expanded and all of that. New forces come in. Like we would not have known that it was accelerating. The accelerating of the universe wasn't evident in the first few billion years. Only now could we see that. There could be other forces that won't come into play till then. Also, the physics could be changed. The Higgs field, which gives everything its mass, has a value of 256 GeV. What if it spontaneously changes? There's no reason for it to be that way. It just got set that way at the moment of inflation. For example, what if it decides to reset to 42? You caught it, right? If you read Hitchhiker's Guide to the Galaxy, you know that that's the answer, 42. And you want to know the question? Well, there's the question. What's the Higgs field going to become? So you don't have to read that book now, if you know how to do it. The theory that I like most is Linday's theory of baby universes. In this, he says that vacuum fluctuations are always going on, and particularly at the time of inflation, in the early time. So as our universe expanded, there could be vacuum fluctuations that were massive, and in the space-time fabric itself, they decoupled from the universe. Baby universes were spawned by our universe. Some of those universes that we have no contact with them, some of them will be sterile and lifeless because after they undergo their own inflation, the laws of physics will be such that life could never form. Others will be able to form life as we know it. So we'll have baby universes out there with little Earth-like things and creatures that might have 6 fingers, whatever. And maybe still others will be conducive to life as we don't know it. But there'll still be life there. I'm almost done. This is the last few graphs. You can read my book. Okay, so there's also super engineering that could come in to save us. Maybe we could find a way to reverse the expansion of the universe. If you're familiar with civilizations, a type 1 civilization can fully control its planet. We are not type 1 yet, but we're on our way. We've already reached the point where we can destroy our planet. A type 2 civilization can use the full power of its sun for what it wants. And if we saw one, it would show itself as what they call a Dyson sphere, which would be a lot of solar detectors all the way surrounding a star, and you'd only see it in the infrared. A type 3 could utilize all the power of its galaxy. And I'm thinking, this is me now, that maybe we could type 4 could get the full power of the universe and use it to save ourselves. Like, what could they do? Maybe they could find a way to interact with the multiverse. And and how to make these little wormholes, maybe this dark energy could be used to create it. So that's it. That's the hope. Now, I know we got some students here in physics and maybe philosophy and chemistry. This is your goal. This is your assignment. Find a way to make one of these things happen. And so my time is up in many ways. Your time's just beginning. And so, thank you.